Welcome everyone, and thanks for the interest in our talk. In the next 30 minutes, we're going to talk about the future of digital identities, and we will use the Kingdom of Cheese as an example of how identities work. So first, I am Patrick. I work at Ubique since 2014. I started as a student while I was studying physics at ETH. And currently, I'm doing something like security engineering and supporting our backend team.
I'm Cléa. I also studied computer science, probably as most of you at ETH. I did my master here, and after a couple of years working in the private banking sector, I joined Ubique at 2017 as an Android developer, and a couple of years ago I started also to do some project management on several projects. So at the moment I'm working currently 50-50 on those two roles. So I have kind of a split role which I'm working day to day. So a few words about Ubique and who we are. We are based in Zurich, near to Central and near to ETH. We have still a lot of students also from ETH which are coming to work at our offices, also because they're near, for example. What are we doing? Probably most of you know our products or have them on their cell phone. SPB and COVID Certificate are probably the most installed apps in Switzerland right at the moment. And you might be asking, why are they doing a talk about security and also like self-governed identity? What is the reason for it? The reason for it is we don't want to see how something gets implemented. We want also to be involved and educate ourselves and educate other people which pitfalls and which issues can happen in common patterns. And we want to show the people this and also make them aware that you can protect your privacy and the security of those systems if you think a bit ahead of the naive approach we're going to show you. Just a few numbers to Ubique. We are founded in 2010 in Zurich. We are around 50 people. We are still growing, and we develop everything in Switzerland, so we have no other nearshore or offshore developers. But now let's start the reason why we're all here.
So in the beginning, we will start with a somewhat naive approach of how to digitalize the current state of the art of issuing passports and documents. So we will start with our sample case, which is like Jenny, the mouse. She wants to be very modern and get a digital ID. So she wants to go to the government and asks for this digital e-passport. After she gets the e-passport, she's now open to do stuff in this digital world, and she can get a residence confirmation, for example, from the townhouse, to, in the end, then go to a bank, present both of them, and actually get a digital bank account without ever leaving her home.
So let's have a deeper look into these steps. And again, I want to repeat that this is a straightforward approach. It has some flaws, and you may be also already challenging some of those thoughts. If you do that in your head, we're going to go back and show you what are the issues we see. So the first step is Jenny needs a decentralized identifier. This she's going to get with a mobile app, which is done by the government, and it's a wallet app, and there she can basically do her decentralized identifier. This is going to put on a ledger. You may be asking, why on a ledger? So using the technology of blockchain for this matter to share public keys is at the moment the best way we can do it, because it's also decentralized systems and it's not on a centralized server where when it gets hacked we have an issue. As a next step, she's going to make a trust with her government that she can issue her e-pass. And the government, she maybe has to go to the government, or they have another technology how they can trust her. After that, they send her a QR code. This QR code, she is going to scan in her wallet app again from the government, and then she will get her e-pass, which is digitally signed by the government. Also, their decentralized identifier is on the ledger. So what can she now do with this e-pass? What is in it, actually? So it's signed by the government with their decentralized ID, as I said. It contains certain claims about Jenny, so her age and also her name and other information. And also she can verify with the public key, which is on the ledger, that the signature is correct from the government.
So now that Jenny actually has this e-passport, we're going over the step of getting the residence confirmation. So she can now use the e-passport, which is signed by the government, to present it to the townhouse, for example. We call this a verifiable presentation. So what does she do? She uses the e-pass, which is signed, and signs this whole package again with her own private key. The townhouse then can first check if this presentation was actually signed by Jenny by looking up the public key on the ledger, and if the e-passport was actually signed by the government by looking up the public key of the government on the ledger. By checking the subject claim, for example, in the e-passport, she can be sure that Jenny, which has this DID on the ledger, is actually the one who was the recipient of the e-passport. So now the townhouse is sure that the presentation they got is actually by Jenny or from Jenny and can issue this residence confirmation.
So now at the final step, let's open her bank account. For this, she has again to send her residence confirmation and her e-pass to the bank. This she signs like one package. The bank can again check if all the decentralized identifiers are correct and see if the residence confirmation and the e-pass belong basically to Jenny, and after that they can open her bank account. So I hope that you all saw the flaws and the privacy concerns we're going to address here and the security concerns in now this naive approach, but I go through it so we can agree that there are issues. So the first issue we see is Jenny always shares her whole e-pass, which is not really necessary, as she, maybe for opening a bank account, there is no need to know her gender, for example, or other stuff. She doesn't want to show this. This problem we're going to address by solving it with the selective disclosure. The other problem is the decentralized ID can help to match stuff about Jenny, so that it's on the ledger, so everybody has access to it, and two third parties can talk with each other and exchange the information based on the signature because they know it belongs, all this stuff, to Jenny. The last step is also we want to hide the signature, because when you maybe buy something online and you don't, for one good you have to give your age and for the other one not, you don't want them to make a register of you as well. So let's start with the selective disclosure issue.
So what's actually the problem with selective disclosure? I mean, in an analog world, we also show our passport, right? But in the digital world, it's much easier to get, for example, copies of it and other gathering of personal information, and there's much more information available on the internet. So what we actually want to do is we want to, while presenting our e-passport, we want to make sure that the party who receives our e-passport, the signature thereof, can only see or verify certain properties on this e-passport. So in this selective disclosure scheme, we can actually only reveal certain properties. For example, on the e-passport, when we show the e-passport, we can make sure that the recipient only sees our name and not the age, the nationality, the gender, and so on. With this, I hope it's clear that we can improve data privacy, because now we are in control of what we show and what we want to share about our information. So currently, we have this problem. Most digital signatures, as you probably know, are based on RSA, or elliptic curve digital signing algorithm, ECDCA. And those don't, in this like naive way, support this selective disclosure. So what could we do? We could, for example, start issuing certain properties by themselves. So let's take this example of Jenny, who wants to sell the Bordeaux wine to get some more cheese. So she has this Bordeaux from 1980, which was apparently not a very good Bordeaux vintage. But she has this other wine, which is like super bad, but has this super nice Bordeaux vintage of 1964. So if we would sign each credential by themselves, Jenny could just take any two of those 4 credentials and combine them to present to Thomas, for example, this Bordeaux, which apparently is from 1964, which is obviously not true. So the very naive approach, or the easy solution to this problem, would be to just sign any possible combination of credentials. This might work for 2 credentials because there are like 3 different possibilities, but it scales very fast with n. Actually, it scales with the power with 2 to the power of n minus 1. So as soon as you have more than 5, 6 credentials, it's getting really messy to have all the signatures. So there are other ways to get the selective disclosure done, and we are going to talk about the common initialized SCIA signatures, which are also RSA-based. But there are also the BBS plus signatures, which are based on a mathematical concept of pairing, which is much more complicated to understand and verify, and hence we only look at the CL signatures.
But first, we're going to we address the other 2 topics because they have some basis you will need for understanding the CL signature. So for repeating, we want to hide the decentralized identifier. So why do we want to do this? Is, for example, Jenny has maybe 2 bank accounts. She has one at the E-Cheese Bank and one at the bank, or the National Bank of the Kingdom of Cheese. And now they're going to talk with each other, and they can find out with the decentralized identifier on the ledger that Jenny owns 2 accounts, which we want to avoid. So the goal is to hide this identifier so Jenny can choose herself when she wants to link those 2 accounts, so the credentials. So if she decided she wants to show that she owns 2 accounts, then it's her decision and not the decision of a third party. So the naive approach would be, again, to use different decentralized identifiers to get the credentials, which is not actually what we want, because then we cannot link them anymore. So it would also not be okay. So what we have is, as a solution at the moment, is link secrets, which can be approached by the Patterson commitment. And these link secrets have to follow requirements. So Jenny, first of all, wants to blind a secret. So she wants to hide what her secret is. And also, she wants to use the secret multiple times. She can also prove that she knows the secret, that she is the subject for it. And also, she can use the signature more than one time. Also, she can show, sorry, that's the other way around. She can show that one or another signature or more signature use the same secret. So how does this now work? Let's go first 1 step back to the analog world. Let's imagine Jenny loves to go to race cars, and she wants to bet on the pink car, but she doesn't want that Thomas knows on which car she's betting. So she makes a seal on her envelope, and they cannot be open. After the race, she can open and show Thomas, "Hey, I bet on the right car." So how can we achieve this in the digital world? So we're going to use a cryptographic elliptic curve, G, as our base group. Then we take out G and H out of this elliptic curve, and those are our public keys, so they will be known to everyone. Out of this, we can formulate a commitment which contains X as a secret and R as a blinding factor, so we can not reconstruct from 2 commitments the secret out of it. And with that, we now have we can hide our secret. So how does it look now on the case we're going to be, So this now fulfills following properties. First of all, there is no other X which will be the same commitment as for an X prime, so we are sure it is not the same. Then we can hide the secret X, and we will not leak any information with our commitment. And it's adaptive homomorphic, so we can use this property to show exactly what we had before in the requirements, that two commitments use the same secret. So this is a couple of math, but it's not, if you follow the slides after it, you will see it's easy to understand. So now we have shown that all the properties which Jenny had, the Peterson commitment will fulfill. So what does it mean now for the car racing in this world again? So Jenny will get G and H and will put this on public so that everybody can see it, and then formulates her commitment. Also the C will be pushed to a ledger or where everybody can see what the commitment is, but nobody knows her X and R. So the secret, the X is the car she bet on, basically. After the race, she's gonna reveal the X and the R, and now Thomas can check if it is correct what she was initially stated in her commitment.
So before we're going to show you some ideas of zero-knowledge proofs to actually show that we know the secret of the commitment without revealing it, we firstly going back to the third problem we had, namely the hiding the signature. So imagine for now that in the kingdom of cheese, there's a web page, something like a web shop, for example, like Amazon, where you can buy everything, like all the goods. And Jenny is a customer of this web shop, and she buys certain stuff. For example, she buys something where she has to prove her nationality to be part of the kingdom of cheese. But then on other occasions, maybe she also wants to buy something where she has to prove that she's over 18. And by always using the signature on the same web shop, she can Selective disclose certain properties, but the web shop can actually aggregate all the signatures and in the end correlate the signatures because they are the same. Can correlate the signatures to the same properties and gather all the information on the e-passport. So what do we want to do? We want to hide the signature. We don't want to present our signature. We only want to present the knowledge thereof. That's where we are going to use the zero-knowledge proofs. And we call them proof of knowledge because we prove without revealing the signature that we own a signature which is valid. Yes. And with this, we can actually eliminate the link between different signatures because we're now not presenting our signatures when we buy stuff, but we present a zero-knowledge proof of the signature, which always has certain random parts to it, which means every proof we present will look differently. And hence, there's no way to actually combine different signatures to gather all the data on the e-passport, for example. We will now show this so-called Schlor protocol, which is basically one of the bases of all the zero-knowledge proofs, or most of them. And we use it to prove that we know the secret to the Peterson commitment without actually revealing the secret. What we actually do with the Schlor protocol is we prove the knowledge of the discrete logarithm. So this works in like any group you have, you can prove this discrete logarithm that you know it. And it's actually an interactive proof of knowledge, which means the prover has to interact with the verifier in order to agree on the proof. So how does the Schlor protocol work? So we start with our commitment C on top, which we already know with the public key G and H, right? And in the first step, the prover initially chooses beta and gamma at random and creates or calculates this new group element A, which is composed by A1 and A2, which is basically just the two random values multiplied with our generators G and H. And we send this to the verifier. So the verifier now saves those two, this point or this group element, and chooses a randomly unguessable C and sends it back to the proofer. Now, the proofer calculates the values S1 and S2 based on combining the secret value he chose in the beginning with the challenge and the secret value of his commitment, and sends it back to the verifier. Now, the verifier can just calculate a new C prime by using all of the public parameters, namely S1, S2, the challenge he chose, and the commitment, plus the public key G and H. By multiplying the S values and combining everything, we see that in the end, we again get the initially chosen base group element A, which now concludes our proof. So this way, we actually, when we go to look what we publish A. There's no information on X in A. And we publish S1. There is an information about X in S1, but it's hidden because we can't solve, or we assume that we can't solve the discrete logarithm problem. With that, we're going over to the Kamenisch-Lisanskaya signature scheme, which is a signature scheme which also uses Pedersen commitments and zero knowledge, the Schlor protocol to prove knowledge of a signature or sign certain stuff. So let's go back to the actual problem we had, right? We had this problem that Jenny wants to sell her Bordeaux wine, but claiming a different vintage. She was claiming that the Bordeaux was from 1964 when it actually was from 1980. So now with the selective disclosure, we can issue a package of properties and reveal ourselves what property we want to show, so we don't have to use atomic signatures as we used for this flawed example. The Kamenisch-Lisanskaya signature is actually based on the strong RSA assumption, which means all the assumptions usually which are true for the RSA algorithm are also true for the CL signature scheme, which also means the weakness to the algorithm are the same weaknesses as to the RSA signature scheme. With the Kamenisch-Lisanskaya signature scheme, we can actually sign commitments. So we can use a blinded signature, which we can use, for example, for hiding the DID. We can partially reveal certain properties in the signature after we got the signature, which enables us to selectively disclose our properties. And last but not least, we can also prove that we know that we are in possession of a valid signature without actually revealing the signature, which gives us the third property we had, the hiding the signature. So now we shortly going to walk through the different steps in the signature scheme. Firstly, we start with the key generation and go over to signing and then the verifying procedure. First, since it's RSA-based, we choose an RSA modulus n, which is composed of two prime factors p and q. And obviously, those p and q have to fulfill the same properties as for the RSA algorithm, namely, they should be safe primes. At next, we choose randomly from something which is called the quadratic residues, which is just part of the same group, but has the property that there exists a b, such that b squared equals to a. And we choose a1 up to al, the number of properties we want to sign, plus b and c. Now we have something which we call the public key, which is based on the RSA modulus n, the a1 to al, the b and the c. The private key for our signature scheme is now the factorization of n, as in the RSA algorithm. Now, how do we actually sign something? So on message input m, for example, the M1 and M2 from the Bordeaux wine, namely the origin and the vintage, we choose at random prime number E and the secret value S. Now, after that, we calculate V such that the equation V to the power of E equals to the product on the right side, and output the signature, which is S, the secret value we use for the B part of the public key, E, the prime exponent, and V, the value we calculated by inverting the product. Now, note that to invert the product, we actually have to know the factorization of n, because we can only invert e, namely the 1 over e, if we know the Euler-Torsion function, which is basically equivalent to knowing the factorization of n. So now we want to verify that the signature is a valid signature. And in the first step, we initially play the same idea of Jenny sells the wine to Tom, so she has to reveal all the properties because Tom wants to know everything about the Bordeaux wine. So first, Thomas checks that the equation holds, that v to the power of v equals to the product. Now note we have v, e, and s, which is part of the public available signature, and we have m1 and m2, the properties Jenny reveals to Tom, and we have the public key a1, a2, b, and c, and the modulus n, which means we have every part of the equation, so we can actually verify the equation. There are certain length requirements on E, but for the concept, they're not that important. Now, Thomas can actually calculate it and now knows that, yes, the S, E, and V values he got from Jenny are actually a valid signature on the public key A1, A2, B, C, and N for the messages M1 and M2. Now, Thomas has bought the wine and everything worked out, and now he wants to join the Bordeaux Club. But since he only owns this 1980 Bordeaux, which is not a super exclusive one, he wants to hide the vintage of the wine. And of course, for the Bordeaux Club, you only have to own a Bordeaux and don't have to reveal the vintage. So what he does, he formulates a commitment. He formulates a commitment to the vintage of the wine using the message M2 and chooses a random factor R to hide his signature, his commitment. He then modifies the signature he originally had, the S, E, and V, to be S minus R, E, and V, and publish it and shows this new signature to the Bordeaux Club. Now, the Bordeaux Club can calculate again the product because everything on the left side is known. The V and the E is the same, and on the right side we now have the message M1, which is the origin Bordeaux, and we have this commitment C, which is actually formed by using the public key A2, the public key B, and M and R, combined with the new S value, S minus R, and we can see that we, in the end up with the same signature S, E, and V, which is the right-hand side. So Thomas now has proven that he knows that he actually is in possession of a valid signature without revealing the vintage of the Bordeaux wine. Of course, further, he probably also should prove that he actually knows the value, but he can do that with another Schlor protocol round. Yes.
So let's recap what we learned in this half an hour. We learned how Jenny can open a bank account in a digital world, and we looked at several issues we addressed with you. So the first issue was that Jenny doesn't want to reveal all her properties. This we have done with the selective disclosure. Then the second was that we want to hide the decentralized identifier, which we have done with the Patterson commitment. And the last one is we wanted to hide the signature so nobody can track her buyings on the internet or on a web store. If this was now a lot of theory for you, that's okay. If you want to check out how this looks in code snippets and try a bit out this stuff and also review the slides again, please scan the QR code. It's a public repo where you find everything and you can check again what we talked about today. I thank you for your attention, and please, if you have questions, ask.
Just one note, because we don't have more microphones, please repeat the question after someone's asked.
Yes?
Why should the identity be decentralized? It's issued by the government anyway. Then do we not introduce this risk by putting it on a ledger? Like the ledger might not always be there in the future.
Yeah, so the question was if the identifier has to be decentralized or if we expose more risks by decentralizing the identifier. So the whole concept of this self-sovereign identity is actually that people who want to have an identity own their identity. The ledger is just one way of publishing the identifier, but basically this is not really needed. It's only needed for public figures like a government who wants to be able to prove that it's the government and you have valid credentials. But the whole idea is that no one owns your identity. That's the point. Because you always own the private key on your phone. You never publish it. There's only a public key somewhere, or you can send it to someone, for example. If you have other trust mechanism, you don't need to put the public key on the ledger. You can just send it to someone per NFC, Bluetooth, email, whatever. Does that kind of answer your question?
Yes, I think it was just for the bank example. They would want the government-issued identity anyway, like not like an identity that we have for ourselves, but issued by our government.
The thing is, it's not the identity who's issued by the government. The government does not own your identity. That's the whole idea of the self-sovereign identity. The government only owns credential properties like knowledge about you, which can be linked with your identity.
But then how am I going to certify that my identity is not a lie? Like I made up my name, for example.
That's the initial trust. So that's the question about how do you prove that you are yourself to the government. And this is the initial trust. It can be done by that you go to at the moment you have a passport, so at some point you're going to switch this to an e-pass. And you probably have to go to a government to do this first step. The initial trust is done still physically or over a video call with certain banks already doing it. So the initial trust is going to be...
I mean, you're right. There's always a problem of this initial trust. The whole community is only concerned of how you can use this identity once you established this mutual trust. But after that, you're the owner of your identity. And with signatures, you can prove that certain properties are actually belonging to you or someone credited for your identity.
Thank you.
Yes?
Is there any possible mechanism, like if you lose your secret key, you just cease to exist on the internet, or
So the question was if there's a mechanism for backupping the secret key. I mean, there, of course, you have this thing you always have in the private sector. You have to weigh the privacy and security of your system with the user experience. So usually you would say, yeah, maybe there is an option to actually back up your secret key. Like, for example, Apple is doing with this FIDO credential, the passkeys they introduced in the last developer conference, where the secret key is kind of stored in the trusted platform module, but somehow exportable that you can actually use a new iPhone and sign in with your account and get the new secret keys. So such a mechanism, for example, could be a possibility, but you always have this kind of a problem. I mean, if we have solved the problem of this initial trust, then of course you could always go back to the government or somewhere else to get this initial trust again and publish a new identity or a new decentralized identifier and use that from that on. Like you would do now, right? If you lose your wallet, then you have to reissue all your documents, like your credit cards, your passport, your ID. Basically the same idea. Yes?
I understand that you would want to hide correlations about yourself on the internet, but there are many other ways to get correlations about a user
It's the question. So I think, the question is, why do we need to hide our decentralized IDs on the internet, or why is there a mechanism for it? The point is, and why we are doing something, because there are other big players which are gathering our data at the moment. Does it even make sense? And I say, that does make sense, because we have to address these things. We cannot just leave it open to the big guys to decide that they can gather our data. So I think, yes, we want to protect the people that the data is violated and used for other stuff. So I think, yes, it makes sense, even if you start small, but the final goal has to be that our data is our good and nobody has the right to track it. So.
And further, there are also mechanisms to use the zero-knowledge proofs to a much further extent, such that you, for example, don't have to show your date of birth, but can show a proof that you're over 18 and other stuff. So sure, you could correlate, but the less you can correlate, the better, because it's already done and we don't want to worsen the situation.
But doesn't this worsen the situation of being tracked online? Because right now you can just enter a name and you need a credit card. And if you would have a signed ID or signed name, then you know that that's that person's actual name, and you can actually match that against other purchases, for example, if you use your identity on different web shops.
So the question was if it's worsening the situation by using a digital ID compared to signing up with a random username and a credit card. I mean, basically, as soon as you use a credit card, you use something which is linkable to yourself, which in the case of the credit card company, in a way, puts the whole governance of your data in the hands of the credit card institute. For example, you have to show your credit card number, you have to show your CVV, and you have to show your name and the issuance or the expiry date of your credit card. When using a digital identity, there are mechanisms to actually hide that and only show that, for example, MasterCard or Visa has issued you a valid document, and you can use this, for example, hidden credit card number or hidden CVV to maybe use multi-party computation to actually be sure or match again in the system of Visa or MasterCard the transaction again, but you as a web shop never sees this data. So that's a mechanism which is absolutely not possible in the analog world, because you have to have the number. And I think if done well, you can improve the situation rather than worsen. But you're correct. And that's what Cléa in the beginning wanted to point out. If we just let the digitalization happen and don't interfere and don't interact and don't pose such problems, then we will end up with a bad solution, like a worsened situation where everyone can gather all the data. For example, like something like cyberpunk, where you have this e-commerce, this super capitalistic society which is only about ads and selling you stuff.
Yes.
Does this system offer chances for interoperability? Could you go to a different country and use, because the risk is that every country makes their own system. For example, if you want to go to a different country and buy something there or identify yourself there.
So the question was if this is interoperable with other countries. So I kind of smile because we had this problem quite 2 years ago. I don't know when it started, Covid Certificate. This was the same problem. We wanted to have a certificate which works all over the world, and not each country makes their own certificate. And at the end, there was European government who decided that there is a certain scheme we have to follow along so that it is working with all the other parties which are involved, and we can travel around the world. And this will be probably also necessary, that all the countries agree on one scheme so we can use it all over the world.
What we were like conveniently not telling you is that there is actually a W3 consortium which is concerned about digital identities and also has published schemes about the verifiable credentials, verifiable presentations. And there is a community working on it. And there are also prototypes or proof of concepts, for example, in British Columbia, where you can get a digital signed driver's license, which uses the Hyper-Indy ledger. So there is this idea, and every technology we saw in our research is actually trying to follow this W3 standard in one way or the other. So yes, it's a huge problem, and we have to agree on it. But I guess we also had to agree on passports at one point.